Thanks everyone for coming to the Go Meetup this month. I'm Andrew. I'm going to talk about deduplicating data with content-defined chunking. The motivation here is that we're trying to deduplicate data. We want to find common parts of similar or related data sets so that we can save disk space when we're storing a bunch of copies of similar data, or if we're trying to send something over the network when the recipient already has similar data, we don't have to send it all. For example, it's nice if you can back up your laptop regularly. Maybe you want to back it up every hour, but you don't want to have to buy a new hard drive every hour to hold the full backup and have to wait for the entire hard drive to be copied. Maybe you have a bunch of virtual machines or container images and you've got the same base OS, you've got a bunch of libraries and applications installed that are all the same across all these things. And you don't have to store the content a bunch of different times. And then there's software updates as well, both source code and updated application files. So basic thing we want to do here is find the identical bytes, find the changed bytes, be able to tell the identical versus changed bytes between different versions of large data sets, and then send or store only a reference when we know that we already have a copy of some part of this data. So I'm going to talk about a sample data set, and then I'll show a few different algorithms for deduplication. We'll start with just file matching, aligned block matching. I'll show Rabin-karp rolling hashes. Then we'll get to the promised thing in the title of the talk, content-defined chunking, and summary questions, and we can dig into the code if people are curious as well. This is just unoptimized proof of concept code I wrote in a couple days, running on just a single data set. So the results we get, they're roughly in line with what the theory says would happen on much larger data sets, but we're only running stuff that all fits in memory, runs in just a few seconds. So like the high level conclusions should be, are things we should be able to extrapolate from what we're looking at, but anything that's really specific, like, oh, this performs 3% better, just not a valid conclusion to draw from what I'll show. But hopefully it gives like the overall theory. Because just things are a lot different when you're talking about tens of terabytes of data that you're trying to store than just a few gigabytes. In the real world, if we were doing this, we could test on lots of different data sets that are representative of the kinds of data we were aiming for, like, oh, are you really caring about backups or virtual machines or virtual machine backups, or that sort of thing. There are existing libraries. I'm not using any content-defined chunking libraries, but there definitely are some out there. You can dig into the literature. Lots of people have done research on these topics. They write papers full of interesting tips on how to make this perform well. And we're just going to look at the amount of data deduplicated and a bit at runtime. But in a real system, things like memory use, how many round trips you make in your network protocol, that's all important. And I'm going to focus on the core deduplication algorithms, but there are lots of other interesting things in this problem space around how do you store the metadata, how do you build efficient network protocols, and so on. So all very interesting, but we're just going to talk about the core deduplication stuff. So the code's written in Go. Here's a link to the slide deck and the code. If you want to type the whole thing in, codeberg.org/AndrewN. There's just one repo there for now. And I made a QR code for people who want to try to look at the code on their phones. As I said, I didn't use any libraries because I just wanted stuff to get working. But I found Go was a very nice fit for the problem space. It was really easy to work with the byte buffers, the maps, write code that loops over them. I didn't have to worry about when the memory was going to be freed because the garbage collector took care of that. Having the built-in tar library was very nice. So was having the reader interface. So it was nice that, at least for this problem space, it was something where it was much more, oh, I'm just using the language without having to really think about it. Then sometimes when you're like, oh, how do I do this in this language? How do I get around it? So just very, very nice fit for the problem I found. I'm just going to try to define some terminology that hopefully makes the rest of the talk clearer. So the data set that already, I'm assuming we've got two data sets. This generalizes to a bunch of different related data sets, but we'll just look at the case where there's two. You say there's the base and the update. So we already have a base data set, and it already exists on the backup drive or at the receiving end of the transmission. And the update is some other data set that has some overlap, and we're trying to store it or transmit it efficiently. So got base, update, trying to find stuff in the update that's already in the base. chunk and block and window, uh, for the purposes of this talk, they all mean exactly the same thing. I use them in slightly different, I use the different words in different contexts for not great reasons. So just if you're thinking like, oh, he said chunk there, now he's saying block. No, no, it's all the same thing. It's just a sub area of the file contents. Things like, oh, we're looking at bytes 1000 to 1999. And hash and checksum also mean the same thing in this talk. I'll try to only say hash, but if I slip and say checksum, just pretend I said hash. So the sample data set I'm using is, well, the two sample data sets I'm using are different versions of the Linux source code. So one is just the dump of a recent long-term kernel. So it's recent updates to something that was forked off 3 years ago. And then the other one is like just the main branch, the very latest thing. So there's going to be a lot, well, there should be there are going to be lots of changes between the two because lots of updates have happened in Linux in the last 3 years, lots of development, new drivers, new things. But they should still be pretty similar because it's not like the whole kernel's been rewritten or fundamental architecture's changed. There should be a lot of similarity between the two. So go code to read. Yes, you have a question. Go ahead.
On tart or hard?
Sort of answered in the next slide. So reading a tarball in Go, you say tar new reader, you pass in basically like the file handle. You get an iterator that gives you these headers for the different files packed into the tarball. And then there's info, and it's pretty easy to read the buffer. So I decompressed the files because otherwise it took like 20 seconds to unpack them. So the files are decompressed on disk, but Go just loops over this, and then I'll show you, it is super fast to just, the base version has 1.3 gigs of data, and the update version has 1.5 gigs of data and 92,000 files. And if I run it again, it's even faster because stuff's cached in memory. It takes half a second to run over all of those. And when we do other things and say, so this is like skipping ahead through pointers in memory in the file. But when we want to actually look at the file contents as well, that's really easy in Go. It's just this, I forget the exact code. We might see it later, but it's really easy to say, give me a byte slice pointing at the place in memory where all the data for this file in the tarball is. So the naive approach is we have 1.3 gigs of Linux kernel source code, and we want to also store this updated version. We could just copy over the whole 1.5 gigabytes and not do any deduplication, and that's what we could do. But we can do something a little bit more intelligent. So the first thing is doing file matching. Does everyone know what SHA-256 is? So SHA-256 is a hash algorithm. It's intended to be a cryptographic hash algorithm. So some hash algorithms are more likely to have collisions than others. And so the cryptographic hash algorithm is meant to be something where it's effectively infeasible for someone to come up with some other piece of data that has the same hash value. So when you're using like RSA or SSH or things like that to do digital signatures, usually you're not signing the whole set of data yourself. It's you take the SHA-256 or another similar hash algorithm of the data and then signing that instead. So it's a way of taking a file that could possibly be very large and crunching it down into, I think it's 32 bytes, in such a way that pretty much every file that's different is always going to give you a different result. So when we do that, just while we're looping over the files, it's io.readAllTr is how you get here. Give me a buffer, like give me a memory buffer that has the contents of that file I was looking at. So the hash, we take the SHA-256 hash and we store it in a map. And then this is while we're scanning the base file. And then in the update data set, Again, we just compute the hash of the file, and then we check, hey, is this already in the map? And if it is, then we increment a counter. So we can put some stats, and if we run it, then it is also very fast. And so 30% of the hashes, 30% of the file hashes were found. 29% of them were at the same path. So this is able to catch if files move around a bit. And similar number of bytes. It's a little different because like not all the files were the same size, but we were able to find that, 27% of the bytes, so 400 megs that we would save are just files that are exactly the same between versions, but they may have moved around a bit. So that's an easy thing. Two data sets, just take the hashes of the files in both, compare them, and use that to deduplicate. So the issue with that is that only works if the files are exactly the same between the source and the destination. If there have been any edits to the files at all, we're not able to deduplicate them at all. So next step up from that is aligned block matching. So we look at the hash of the first 1,000 bytes, we look at the hash of the second 1,000 bytes, we look at the hash of the third 1,000 bytes, and we get more hash values, but there's also more things to compare. So the loop here is, instead of taking the hash of the whole file, we loop over chunks of at most block size bytes and store those in a map, look them up, and when we run that, we are going to get better results. I think we were at 27% before, and with this, now we're at 36%. So just looking for cut every file into 1,000 byte pieces. Now we get like an extra 6% overall data found. So this is great for, so this is catches the cases, the same case before, where if the base and the update have identical files, we catch that. If the update adds or removes some data to the end of the file, then we're able to see, oh, the start of these files are identical. And if there's some edits in the middle of a file, then we get the same stuff before and after. Yeah.
Question: Is this function with always loading everything into memory, or
This is all done in memory here.
so is there you need to have enough memory available to load the entire data set at once, or it is reading in chunks?
This implementation actually reads things in chunks. So it reads in the input, and every 1,000 bytes it reduces to a 32-byte hash, and it stores them all in a map for the base. And then on the update, it reads 1,000 bytes at a time, and it does a hash lookup, and whether it's found or not, it just throws it away. So yes, yeah, you need enough memory to store the hashes of everything.
Not the full file.
Yeah, exactly. Yep. So aligned block matching is very effective for virtual machines where when your deduplication block size is a multiple of the disk or file system block size. So if you've got 20 virtual machines that all have the same operating system file in there, they're going to have the same data 20 times, but it's going to be spread out in different parts of the file just because of where the file system chose to allocate it. But in the raw disk image, all those chunks of that file will show up at some multiple of the file system block size. So here, the example, if there's some yellow data and there's some orange data, and it's moved around in other places, as long as it lines up, it'll be found, it'll be deduplicated. However, if some data got shifted so that it's not on a block boundary, then it won't be found. So that is sad. That is sad. If you take a file in the base and you just add a little bit of data in the middle, that throws off the alignment of all the future blocks. So you won't find any deduplication there either, even though it's good. So one naive approach is to sort of handle this case is, well, what if we took not just the 1,000 bytes that are like on the nice boundaries, but what if we just took a hash of 1,000 bytes here, 1,000 bytes, so just at every byte offset we could take a hash, and we would find this here. But it sounds like it would be very expensive, because on a if we have a 1 megabyte file and we take 1,000 byte hash at every byte offset, we have to hash a gigabyte of data. And so hashing is reasonably fast, but if you're hashing 1,000 times the amount of data you have, it's going to get too slow. So it's a shame we can't do that, except actually we can. So let me make this a little bigger. There's a really cool algorithm. It was originally a string matching algorithm called Rabin-karp, but this is a rolling hash algorithm. So it treats the data as a polynomial. So for these characters, these are like the byte values. This is a 7-1 in hex. This is a 6-5, a 6-8. And so we'll compute the hash as 7-1 times 1 plus 6-5 times x plus 6-8 times x squared plus 5-4 times x cubed. We'll say that's the hash value of these 4 letters. And then when we want to do the hash of, when we want to compute the hash of the chunk that is 1 byte moved over, well, we just multiply this by x. We multiply the old hash value by x. We add in the new character, and we subtract this times a multiple of x. And then we've got the hash for the next characters. And so this lets us take a hash for one window and update it to look at the window 1 byte slid over. And instead of having to read all the characters in between, we only have to read the first and the last characters to do that update. So instead of having to look at 1,000 times your data, you just have to look at your data. So here's that written out a bit further. So the hash from 0 to n is this polynomial mod some prime p. And then when we look at the expansion, okay, so that's hash from 0 to n, and then the hash from 1 to n plus 1, and we subtract, it's x times the previous hash plus the last byte minus the first byte times x to the n. Yeah, and so what we'll do with this rolling hash is we'll just take the aligned blocks in the base like we did before, and we'll compute the hashes of all of them, and we'll put them in a hash map. And then in the update, we'll scan along, and at each byte, we'll check the map and say, hey, does this hash appear in the map? And if so, we'll find the block. And has anyone used the rsync command? Yeah, so this is how rsync works. It's doing that rolling hash to look for updated parts of the file. So give me 1 second. I'm just going to have a sip of water. So when we've got the aligned blocks at the start in base, and we want to compute the hash, it's literally just a for loop that says hash is hash times x plus the new character mod the modulus. And so we get the hashes of all the aligned chunks in the base. Then to do the rolling hash when we're scanning in the update, so there's an init block that computes x to the n just by, in a loop of n times, does x times the previous thing, mod the modulus. And then to update the hash when we slide over by 1 byte, we take the old hash times x, we add on the new character, and we subtract the old character times x to the n, and then some adjustment of making sure we don't end up going negative with the modulus because integer overflow. So then the scan is, okay, we're going to look at each character in each file in the update, and we're going to check if the hash appears in the list of hashes we got out of the base. And if it does, because that hash is not a cryptographic hash, it can have collisions, we'll do a second check, just double checking what was the SHA-256 in the base, what's the SHA-256 now, just to make sure we don't have that. And then we update the hash and continue the loop. So normally when you run rsync, it looks for a file with the same name, and then it looks for similarities between the two. So that limits rsync's ability to find similar files, because if you move a file, it's like, oh, there's no file with that name, and it'll copy it again even though it's right there. So you can check everything. So I'll hit run on this code now. Oh, actually, I won't. This is actually slow enough. I have to run it in here because the presentation software seems to have a uh, the presentation software. I think it has a limit on how long code that I run in those little run blocks can run. So let me see. Is this running? Okay. We want rolling hash. Rolling hash. Come on. Rolling hash.go. Run. Okay. Here. All right, so um, it's hashing everything in the base. So I think there are about 70,000 files. So that was fairly quick. So it's doing the rsync style matching of, okay, I'm only going to compare the hashes in the file in the base that has the same name, if there is one, to the current file. And so that runs along. And now, so that actually found 58% of the bytes. So 74% of the files 74% of the files in the update had a file with the same name in the base. And of those, this rsync algorithm was able to match about 73% of the bytes. But because it couldn't do all the files, overall it only got 58% of the bytes. Um, Now, when I let it use the whole set of hashes, it's going to get better results. But as you can see, it's very slow. It took a whole minute to run. But we do get the better performance here of now. It was able to deduplicate 64% of the bytes. So that magic rsync that can look at all the data in the base to pick any part of it to do, it was able to find an entire gigabyte of data that was that was duplicated, that wouldn't need to be copied. So any questions, anyone? I'll just pause for a second while I try to figure out where. Yes. So that's the rolling hash algorithm that rsync uses. So we started with the whole files, we went to the aligned blocks, and then this rsync algorithm lets us do that. The rsync rolling hash algorithm lets us slide looking for matches and gets a much higher deduplication rate. So yeah, here I forgot to cover this. So the modulus we are using is just a randomly chosen 15-digit prime. N was 1,000. That's our block size. And the x I used when I was talking about the polynomial, and this times x cubed is 64 in this case. Multiplying by a power of 2 is really easy for the computer because it's just a shift operation. It doesn't need to worry about remainders and so on. So um, if I go and look here, so when we use the rsync style, just looking at one file at a time for matches, we got no collisions at all on that hash function. But when we use the whole data set, there were 4 hash collisions where there were 2 blocks with different SHA-256 sums that had that same hash with this hash function with the polynomial modulo this large prime. But you know, the textbook I went and looked at for how to implement that was written back before 64-bit computers were common. And so it had a modulus that would fit in 32 bits, but it was only 30 million. It was only 8 digits. And that is something that would be, you'd be much more likely to get hash collisions with. And hash collisions are bad, right? We don't want to do this extra work, but maybe. Like, so the rolling hash tries very hard not to have any collisions, but it can handle them when they happen. What if we had a hash that we tuned to deliberately produce collisions every, 1,000 bytes on average? Then if we had a hash collision, we could say, oh, like maybe this is a chunk we should hash. So instead of this big modulus that's like tried to be like, oh, we I don't know, what is that, like 527 quadrillion, instead of saying like, oh, we only expect a hash every 500 quadrillion bytes. We said, no, like let's have a hash collision every 1,000 bytes. But if we see 2 blocks that have the same hash value, then let's go do the SHA lookup. Then instead of doing that, like it would be expensive to do the SHA lookup on every single byte because you get that 1,000-fold increase in how much data you're looking at. But if you're able to detect, hey, here are two chunks of data that have the same hash value with this lossy hash function that's only going to give us like a 1 in 1,000 chance of matching. If we do the hashes on those, then we're going to find stuff that has, we're going to have a signal to check if these things match, but we're going to have it based on the data. And I'm sorry, I explained this better in my head earlier, but the content-defined chunking is chunks are defined by sequences of bytes with a specific property, such as having a hash of 0 under a collision-heavy hash. So this way we're scanning along, and when we see a chunk of data with this hash of like 1 in 1,000 chance of being a certain value, we're like, well, let's go look for other blocks that are like that have the same hashes. So doing that with an rsync style hash does work, but this is something faster I pulled out of the literature that produces variable length chunks. It's very simple, which is what makes it very fast. So it uses this thing called a gear table, which is just an array of 256 random 32-bit integers. And then the actual hash function is we start with 0, and then at each byte we look at, we take the previous hash and we just do a shift 1 bit on it, and we add in that random value. And then we check if if a certain number of bits in the hash have a mask. So if we're looking for like an 8-bit match, then we're looking for this random pattern in these 8 bits in the hash. And then because we're looking for 8 bits to match, if I remember this correctly, I think that means that, I'm not going to try to do the math in my head when I have it written down, but like a very simple hash function, instead of having to do a lookup in a giant hash table to see, hey, are there any blocks with the same SHA-256, we're just rolling this along, and whenever we see, hey, like the first 8 bits of the hash are all 1, and we're like, okay, this seems like a good candidate to go and look up. So the code for that is, for every byte in the buffer, we take the old hash, we shift it 1, we add in the gear table value, and then if the if we have a hash collision looking only at certain bits, then let's go grab the SHA and then actually go and do the lookup in the lookup table. So if I run this is very fiddly to get the there. Okay, so let me run that again. So it's hashing it's doing the content defined chunking of all the files in base, and then it's okay. Let me run that one more time so you can. So let's chunk all the files in base. Let's chunk all the files in the update, and also whenever we see a chunk, for each chunk, let's go check if we saw that hash earlier in base. And so we got 58% deduplication, so we saved 900 megabytes, but it didn't take a minute, it took 2 seconds. So this is content-defined chunking, and this 1,000 bytes approximate chunk size, that is a parameter. So
one quick correction. After the recording finished, someone asked a question that made me realize I didn't understand part of this correctly, so I took some time to figure it out the next day. The gear hash is not a variable length hash. Because it's a 32-bit integer and the highest order bit gets shifted out on every input byte, it's really only looking at the last 32 input bytes. We're looking for 32-byte markers that match a specific condition, and we're treating all the data between the ends of those markers as a chunk. That fact explains why we have minimum and maximum chunk length parameters. They avoid pathological cases. There's a maximum chunk length for cases like having an input of all 0 bytes where you never get a hash match, and you might say, anytime there are 2,000 bytes without a hash match, just treat it as a chunk anyway. And there's a minimum chunk length for cases where you're getting too many hash matches too often, For example, if you had a repeating pattern of 32-byte inputs, all of which were hash matches, you might say, you only want to call something a chunk if it's at least 1,000 bytes long. Sorry about that, but hopefully this interlude makes things a little clearer.
I'll explain. So with all the examples I gave before, we're using 1,000 byte chunks. If you have smaller chunks, then there are more chunks to keep track of, store in memory, have to wait for them to be looked up. But you also get a higher deduplication ratio because you've got more possibilities for things. So, yeah. But now that we have a faster algorithm, I can show, okay, if we want a if we ask that more of the bits in the mask match, then it will run a bit faster, we'll have fewer things, but we'll get worse results. So this is now down to 45%, but if we go up to if we drop it down to 8 bits that we're looking for. Sorry, let me just run that again. So it's going to be a little slower because it's generating more hashes and it has to look through bigger hash tables for matches. But now we're getting 70% bytes matching, and that's with the average chunk size of 261 bytes, which is close to 2 to the 8. So that's the content-defined chunking. Run compute a hash that's lossy, and then when you see a collision, treat it as a candidate to go and do a check with a larger hash. So just the summary, and remember this is on a single data set, so this is roughly in line with what we'd expect, but like with just a single data set, like it's not going to conclusively quantitatively prove that like one thing's better than the other. But the whole file hash match in this for this data set, we got 27% of bytes deduplicated. Using the aligned block matches, it went up to 36%. With the rolling hash, it was 64%, but it took a minute. With the rsync file matching, it was only 58%, but that was much faster. This is the slowest option because for every byte in the target data set, you need to go and do a lookup in a giant hash table. And that's just slow. Not as slow as doing a SHA-256 of 1,000 bytes, but slow. And then the content-defined chunk with a 10-bit mask, we got 59% deduplication, which is already sort of beating rsync with the file matching on the same block size. And then if we did other experiments, and with smaller chunks that produce a larger number of chunks, we can get much better performance. Let me check something quickly. Yeah, okay. Let me just run one quick experiment here. So this is going to be slower because I'm using very small chunks. They're basically the same size as the SHA-256, and at that point you can just use the string itself instead of the hash. But
that should be the upper bound.
Pardon?
This should be the upper bound.
You can use smaller chunks, but at that point don't use the SHA-256. Just do a direct string comparison. So okay, no, we ran out of time on this, so I can run that experiment later if people are interested. So yeah, having smaller chunks allows better deduplication, but requires more overhead. And content-defined chunking, neat algorithm, super fast. And if people hadn't seen the rolling hash before, I hope you enjoyed learning about it. So the references I have, most algorithms books will cover Rabin-karp. I happened to grab Sedgwick's because that's where I remember learning it from a long time ago. The guy who wrote rsync talked about it in his PhD thesis called Efficient Algorithms for Sorting and Synchronization. So if you want to know more about rsync, definitely check that out. He's written some very readable things about how rsync works. And then these are the two papers that I looked at that I grabbed that gear hash from. And yeah, so thank you for listening to my talk. Does anyone have any questions?
I have a comment.
Yes, I'm happy to hear comments as well.
Maybe you already know this, but you can range over integers instead of doing the classic like preset.
Oh, no, I did not know that.
Yeah, so
Okay.
the I equals range.
Okay.
That's like go 1, 2, or something.
Oh, is that new?
It's somewhat new.
So I defined to be 0. So let's look at the tar one. Yeah. Sure, let's do. So can I do it with a step or?
I've never done it with this.
Okay. Let's look for one where I just do I plus plus then. Okay, so for this one, you're saying for I.
Well, yeah, range 56.
Is it like that?
Just
Okay. Oh, let's make sure I'm running the right.
not that I wanted to like do a code.
Oh no, I'm happy to have the feedback because I.
This is something that I really like about it.
Okay, cool.
Or ranging over, like, if you have like a slice of whatever you have there, like hashes or whatever it is, you can just put that thing in and get that back to you. Maybe you know that.
Oh, yeah. So the range.
Yeah, like that.
Yeah. So yeah. I do a few like loops over sets here and stuff for loops over hashes. Yeah. No, thanks. I did not know about that. So thank you. It's like, the first thing I learned in programming was like the for loop, and then I've typed so many, and I know every programming language, like whenever they do it, like the first feature they add to a new programming language is how do we get people to stop writing those for loops?
Yeah.
Cool. Anyone else have other questions, comments? Yeah.
What inspired you to go down this rabbit hole?
Pardon me?
Well, what inspired you to go down this rabbit hole?
Well, I would like to take more backups more often of things, including virtual machines. And so right now I'm using the Mac Time Machine for backups. And I know at some point they moved to like a snapshot system that's a little better. But the older versions of Time Machine, if you moved a file, you would get a new copy. And if you changed a file, you would get a new copy. So having large files where you sometimes change portions of it or just move them around would blow up your backups. Then you'd have to go out and buy a new backup drive. And so someday I would like to build something that does it or adopt some. I know there are some open source backup systems that are better at that, but just being able to like store backup lots of things. Peter, when Peter runs the meetup, he usually does like intro slides and here's some interesting things from recent Go Weekly. And one of those I think mentioned someone had written a blog post about, or someone had a clanker write a blog post about content-defined chunking. And that seemed sort of interesting to me. And I went and saw the paper and then I'm like, oh, okay, this looks cool. And then, yeah. So thank you. Good question. Cool. Is there any part of the code anyone wants to see, or you've all read it all on your phones already? Okay.
Is there anything that you wrote that feels very idiomatic in Go? Like, is there anything here that you feel like you wouldn't be able to express easily in the language of us?
I think I could do this in other languages. I would be a bit worried about the space. I know Java would definitely have been more verbose, and even other languages like just the way here, like declaring a variable, like there's no keyword, there's no let or something. It's just, oh, if it's a new variable, just do the colon equals. Colon equals means it's new. So it's nice that it was very terse, and at some point the if error not nil. It looks like the IDE, I haven't configured it yet. It looks like it's hiding it for me. At some point, typing all of these might have felt annoying, but the autocomplete has greatly improved these days. And so like every time I would type this, autocomplete would say, do you want the if error not equal nil return error here? And I would hit tab and move on. So yeah.
I saw an interesting vulnerability.
Mhm.
Just like a tiny exposure vulnerability. This vulnerability was in some current, like someone had the standard pneumatic like error colon equals whatever, but they forgot the colon. So it silently worked, but it shadowed a variable. And this
Oh.
was inside a closure. So it shadowed a variable from another thread with no locking or anything. And so you could just erase to make sure that error never received a non-null value. And then you can proceed past an error.
Interesting. So
given that, did you feel like there were any of the guns that you saw?
okay. So closure scope does scare me in Go, because I have messed that up a few times. And I didn't make this concurrent, even though I probably could have, because like once the tar, like when I'm complaining like, oh, like this, it takes a minute to do all these computations, it's completely CPU bound. I probably should just send that out to several threads, but I didn't need to do that because that was the last thing I added, because I had the rsync style and I was like, okay, for completeness, let me add in this thing. And so in general, everything ran so quickly that it wasn't worth the effort of making it threaded. But I know, like, I know it, I know you can make it threaded. It's just, there's a little bit of friction and, oh, I've got to set up channels and stuff. And I know it's easier than doing it in C or C++, but yeah.
Like Rust.
Yeah. Pardon?
Is it in Rust? Is it really easier in Rust to make it find your parallel?
The closure scope would be the closure scope would be a little less scary, but you'd have to deal with the borrow checker a bit, which is yeah. I would say it's probably roughly equal between Rust and Go to make it to make it threaded. I suspect I would have had to deal more with the memory stuff in Rust, whereas here Golang, it's nice, or it's the garbage collector's problem. Yeah. Cool.
I would recommend installing a linter for the variable shadow.
Oh, okay. Oh, it's just when you're looking at my code and you're like, I recommend installing the linter. Are you seeing other things?
No.
Okay.
It was just my eyes wandering.
Okay.
But yeah, the variable shadowing is just bad practice in a lot of shops. They just don't do it. Like the VR doesn't work.
Okay.
And closures aren't the best with like concurrency either. Like I would just not use it.
Okay. Is there a specific linter you recommend?
No.
Okay.
There's like that's a whole topic.
Okay.
That could be a talk.
Okay.
Yeah.
Okay. Because I've had bad experience and I was just checking if maybe there's something I missed, but it sounds like you've also had bad experiences.
There's tons of linters. I don't think the Go community has really like landed on a universal.
Okay.
Some things are pretty standard, but lots of moving things out there.
Okay. Cool. Well, I'm happy to answer more questions or show more code, but if people are okay, I might end it here.
I'd like to know
Oh,
about
yes.
the garbage collector in Go. How is compared with the other languages and how is better compared with other languages?
Oh.
Sometimes can be plus it have what it doesn't have a
That's correct.
You had all the memory by yourself.
Yes.
Like that. I don't know.
Yep.
I don't know anything about the rest.
Okay.
I'm saying about other buffer language that has garbage collector and usually is it's a bad sign. It's a bad usage of garbage collector in other languages. So why Go is good and why is better.
Do you have any thoughts?
It's really hard to say that it's better than a language without a garbage collector, in my opinion. Like, does it have a good garbage collector? Yeah. I think that under certain workloads, it's better than other languages that have a garbage collector. But it's really like dependent on, and it's a newer language, so I feel like it's just like.
Because I come from Python
Yeah.
background and it's terrible. I've heard everybody says that Python collection sucks. So I'm just wondering, like, looks like a good thing.
I think Go has some luxuries being fully compiled in that it can look more closely at what memories we need when and make more adjustments to the runtime. So maybe just by virtue of it being a language, it gets some handicaps.
Yeah, I have only had good experiences with the Go garbage collector, but like I used years ago, I've had a number of bad experiences with the Java garbage collectors, but the algorithms improved over time, and people just computers got a lot more memory, which made it easier because um, like when servers only had 2 gigs of RAM, the garbage collector had to work really hard to like keep everything going. And now, we don't think of we don't think much of, oh, just give 20 gigs of RAM to this, web server process. And the garbage collector has a lot more room to work with. So I did like there are some interesting things about the Go Java collector, and I know they've recently done some improvements, something called Green Tea. I've seen some blog posts, although I don't remember details. It would be a great thing to look into, but like although the Java garbage collector used to give a lot of trouble, I have not had trouble with it in years, and so I think just overall, computers getting faster and getting more memory solved most issues, and now most garbage collectors just work fairly well.
That green tea thing that you mentioned is like an experimental garbage collector in the recent versions of Go. And even then, it's such like the performance improvements are wild in the area that they're testing. But for everyone else that isn't dealing with like that very specific thing, business as usual. Yeah.
Is it
And-
true that Go garbage collector is optimizing for pause times instead of but I feel like 10 years ago or something I read something that the pause times were really short and the throughput wasn't basically something contemporary partners. Am I crazy? I'm not sure.
That's possible. So like this sounds wild to people, but the most efficient garbage collector for Java is one that's just doesn't try to do any garbage collection until the heap gets full, pauses all the threads, and then just garbage collects everything at once and collapses it down. Because that gives you the maximum throughput, but you get lots of really long pauses because it just garbage collects everything. So most of the work in garbage collection and engineering is how do I get shorter pauses that do work but use more CPU time overall, but then the system feels more responsive because you don't have, oh, every 15 seconds it pauses for a second.
Which shouldn't matter at all for non-interactive applications.
Yeah, because I think it's like a GC batch. I think it's called batch GC, and like it's theoretically the most efficient garbage collector, and no one uses it because they just feel bad watching like it stall out all the time. But it's like, yeah, but you're not paying that overhead constantly. So yeah, no, and I know we're always looking for more talks. So if anyone is interested in the garbage collector or wants to do some comparisons or like dig into it, like we'd be happy to have someone present on that.
Oh,
Yes.
quick question.
Yeah.
Did you try out the built-in test libraries at all, or the benchmarking libraries for these?
I did not. So
I was just wondering.
I'm using a hacked version of Go Present
Yeah.
that the tests get mad when I try to run them because all these files have a function main. And so it works for running individual ones, but because they all have their own main functions,
Yeah.
Go test just blows up because it's like you can't have 8 main functions. So it was something where like there are a couple things here where like in the output I just spit out whether I just print out whether something worked or not, where it should really be a unit test. It was like, you know, do I want to just take the easy way, or go off and like get lost in the go present source code again? And yeah, cool. All right, thanks everyone.